Welcome back, everyone, to MAE170. This is week number 5. So for this week, on the menu, there's the root locus method, which I've already mentioned previously. So you might have already seen that I've uploaded the notes for both lectures 9 and 10. In fact, the two are very connected. We're going to cover the root locus method in two lectures. So you'll find just one set of notes for both the lectures. However, I've also uploaded another PDF file named root locus examples, which contains some more examples for the root locus methodology. Okay, so let's try. I'm aiming to cover up to page 10 included for today. Maybe I can do a little bit more, but without further ado, let's begin with the lecture. Okay, so last time we sort of concluded the study of stability by looking at the Routh-Hurwitz criterion. And in the last example, the semi-series design example, we had a open loop transfer function. That is, we had a plant whose transfer function, we can call it g of s. And then what we wanted to do is to close the loop, adding also a proportional controller. Proportional controller is simply a simple gain k. Now, the objective is we want to find the stability characteristics of the closed loop transfer function as this parameter k varies. For convenience here, we're assuming that k is positive or also equal to 0. Equal to 0 wouldn't really make sense, but let's just assume that k is greater or equal to 0. Obviously, for different values of k, we'll have different characteristics for the closed loop poles. And why do I say that? Well, that's because the closed loop transfer function T of S, given this block diagram, is given by k times g over 1 plus k times g. So for different values of the parameter k, we're going to have different poles of T of S. Remember that the poles are the roots of the characteristic equations. What is the characteristic equation? It is 1 plus k times gs equals 0. So if we have k equals 1, for instance, then we would have to solve 1 plus g of s equals 0, and the roots would be the poles for k equals 1. But what about if we had k equals 2? Then the characteristic equation would be 1 plus 2, g of s equals 0, and so on and so forth. You have an infinite amount of combinations, an infinite amount of possibility to choose the parameter k. So technically, you would have to compute the poles for each of these variations, for each of these configurations, making it highly impractical. So if we're just concerned about the stability of the closed loop and we don't really want to know where the poles are, or we're not really interested in the poles themselves, we could just simply use the Routh-Hurwitz criterion. What do? You take the characteristic equation for the closed loop, that is 1 plus k g of s, and then apply the Routh-Hurwitz criterion as we saw. You construct the table, take a look at the Routh array, and check that all the coefficients have the same sign. If that is the case, then the system is stable. If not, the system can be either marginally stable or unstable. What are the pros of the Routh-Hurwitz criterion? It's quite straightforward, simple calculations. And they'll give you information about the stability of the closed loop system for different values of k. If you have just k, you're going to find a range of values for which the range of values for k, obviously, for which the system is stable, and possibly another range of values for k for which the system is unstable. We saw that in the last lecture. For k that was between 0 and 126, if I remember correctly, the closed loop system was stable. For values of over 126, then the system would be unstable. What are the cons of using Routh-Hurwitz criterion? Well, the problems with just using the Routh-Hurwitz criterion is that, well, we can only determine stability versus instability, and we don't really know the values of the poles. So we just know the ranges of k for which the closed loop system is either stable or unstable. But we have no idea that if k is equal to 100, well, what are the actual poles? What are the values? If we knew the actual values of the poles by taking the dominant ones, we could estimate all the performance indices, and so we can have an idea of what the output would be. So the other option would just be pick a value of k and directly compute the poles of the closed loop transfer function, and that is option B. So obviously here, the pro is that you have directly the information about the poles. So you know where the poles are, and it is straightforward to know the stability of the system. For instance, let's say that in last lecture's example, we picked k equals 100, and you'd find that this is, again, I'm just throwing their numbers. You would find P1 and P2 equals -2 plus or minus I, and then P3 and 4 equals, let's say, -5 plus or minus 3I. So you have one value for k, and you can directly compute the values of the poles. In that case, we had 4 poles. In this made-up example, the real parts of the poles are negative, so the system is stable. And of course, we can also take P1 and P2 because they are the dominant poles, and we can retrieve the natural frequency, the damping ratio associated with such poles, and estimate the performance indices as specified a couple of lectures ago. What is the problem with the straightforward direct calculations of the poles is that, as I mentioned earlier, well, it's impractical if we want to change the value of k, because every time you would have to recompute the poles. And this is a big problem if you only have a pen and paper and you can only perform hand calculations. Well, that becomes a problem, because for systems that are of order greater than 2, you would have to solve an equation that is of degree 3 or more. And it is very difficult to solve it by hand. I mean, you would have to solve it numerically anyway, and solving something numerically by hand can get very tedious and very long very soon. So it really only makes sense when you already know the value of k, and then you want to compute directly the poles. However, let me repeat once again, if we want to just slightly change the value of k to see how the system changes, how the system performances change, well, it becomes a little bit impractical. So there's a third option, which is the root-locus method, which gives us the chance to take a look at the bigger picture. And what does that mean? So the root-locus method will give us a way to draw on the complex plane, so on the S-plane, all the possible locations for the closed loop poles of T of S as we change the parameter K. So that's great. You can see all the possible solutions of the characteristic equation as K is changed. So it'll give you all the poles for all the values of K greater or equal to 0. And so you don't have to specify a value of K, compute the poles, draw them on the S plane, then change the value of K, recompute the new poles, draw them again, and do that operation would be highly impractical, as I repeat once again. What are the cons for this method? Well, it's a new thing to learn. So, but that's why I'm here, and that's what we're going to do for this week. We're going to learn how to draw the root locus. That is, once again, I'm going to repeat it ad nauseum. The root locus method allows us to see all the possible locations for the poles of the closed loop system, or the poles of the closed loop transfer function T of S. Now, what are the cons? And another con of the root locus method is that if we have more than one or two parameters, let's say that we had K and then we had I don't know, another parameter M, well, then it becomes a little bit tricky, especially when you have even more than two. Say you have K, M, and N, then it gets complicated. So usually the root locus is used when only we have a variation one parameter or at most two. So if you had two, you would fix one and calculate all the possible solutions for the variation of K, and then you would have to have another root locus for a different value of M. So it gets a little bit impractical when we have already two parameters. So it is a good thing, though, when we have only one parameter that changes. And that is the case for the block diagram that I've drawn here. Keep in mind that this is just an example. It doesn't, the control system diagram doesn't necessarily have to look like this, because the parameter can be also embedded in G of S itself. So in this case, we have K that represents a proportional controller. Remember, proportional because it multiplies the error, so it's proportional to the error. But K can also be part of G of S itself. And well, we're gonna see it later. So anyway, the key thing is that we're gonna have just one parameter that changes, and using the root locus method, we'll be able to compute, and more than compute, visualize and draw all the possible locations for the closed loop poles. All right, so once again here, it's the same configuration that I just drew earlier, so I'm not gonna repeat it. However, I'm going to recalculate the closed loop transfer function based on this configuration. So once again, this is KGS over 1 plus KGS. Another thing that I want you to understand is that here we are computing, or we're visualizing all the possible locations of the poles of T of S by using information only of L of S, or of our loop transfer function. And all the tools that we will develop in this course and that we've developed are based solely on the open loop transfer function. So you get information about the closed loop just using what you have, that is the open loop. And let's see how this is done. So what we're going to do here, we're assuming that g of s, and this is not really an assumption, but because g of s is always going to be written like this, it's always going to be a fraction that has a numerator over a denominator. So g of s is simply n over d. So if we can write g of s in this form, then t of s becomes k times n over d over 1 plus k times n over d. Okay, so let's start with the steps. We're going to have 10 steps for the drawing of the root locus. I came up with 10 because it's like a round number, easy to remember, but sometimes you can find, I don't remember how many steps the book has, probably fewer, but you can also have 2 steps in one, or divide 1 step in 2 or 3. So there's not really a fixed number of steps. I've just came up with this. Sometimes when I personally draw the root locus, I might not even start from step 1. But for you that you have to learn a new thing, it's probably better to have a sequence. But you'll see that sometimes we can do 2 steps at once, or even skip a step. But without further ado, let's just describe step number 1. So step number 1, what we want to do, we want to find or to rewrite the characteristic equation in a so-called canonical form for the root locus. And the canonical form for the root locus is, so delta of s is exactly what we wrote, 1 plus k times n over d equal 0. And here we have our parameter k that is greater or equal to 0. Sometimes you might not have the characteristic equation in this form. Let me give you an example. If you had s cubed plus ks squared plus 2s plus 3 equals 0, well, in this case, the characteristic equation is not in the canonical form. So you have to rewrite it so that it looks like this. And we're going to see an example actually right now of how to rewrite the characteristic equation so that it is in the canonical form. And in order to do that, let's consider what we already know very well, that is a second order system. So we have our closed loop transfer function in the standard form for the second order system, with our natural frequency and the damping ratio. And in this case, let's say that omega n is fixed or is known, and our parameter is our damping ratio. So we want to find all the possible locations of the poles of T of S as we change the values for zeta. So we have to, in other words, solve the characteristic equations as zeta changes. Characteristic equation is the following. And as you can clearly see, this is not in canonical form. We need something like this, 1 plus zeta times a numerator divided by a denominator equals to 0. We want this. In this case, what I called k earlier is our zeta. So what do? Okay, we separate all the terms that do not contain zeta. So it's going to be s squared plus omega n squared. And then the other term is only 2 zeta omega n s. then equals 0. Then we're gonna gather s squared plus omega n squared, because we're going to obtain 1, that's what we want, plus zeta times 2 omega n s over s squared plus omega n squared equal 0. Sorry, should also include this parenthesis. All right, so now this equation is satisfied for either s equals plus or minus I omega n, which is this one, but this does not contain zeta. It's just for a particular value of zeta, as we will see, that is zeta equals 0. So we're going to ignore this. And we're going to just take the second factor, which is indeed in the canonical form. So we have 1 plus zeta times 2 omega n s over s squared plus omega n squared. So in this case, equals 0. In this case, well, k is zeta, n of s is 2 omega n times s, and d of s is s squared plus omega n squared. Very good. So this is step 1. Most of the times, if you're just asked to draw the root locus, you'll already be given the characteristic equation in this form. But if you don't have it in the canonical form, then you have to put it in the canonical form. So that's a necessary step. So now actually, I want to already draw the root locus for a second order system, because believe it or not, we already know the answer. So let's go back to the definition of the root locus. The root locus is the visualization of all the possible locations for the closed loop poles as a parameter changes. So in this case, we have that omega n is fixed, and we're changing zeta, but we already know all the possible solutions. We know where the poles are going to be if we just modify zeta. Well, if you don't believe me, let's go ahead and draw it together. Remember, when zeta was equal to 0, we have an undamped system. Therefore, the closed loop poles will be on the imaginary axis. And then as we increase zeta, then we're going to follow the semicircle in this direction as zeta increases. So on the semicircle, that is, we're going to have complex conjugate poles. Zeta is between 0 and 1. And then these two branches collide on the real axis. So we're going to have repeated roots. Zeta is equal to 1, and the system is critically damped. And then if we increase zeta even more, then the two branches that arrive and collided in this point will separate, one going towards the origin and the other one going towards minus infinity. That is, as we increase zeta all the way to infinity, one pole will be minus infinity and the other pole will be 0. And also remember that omega n for a second order system can be also thought as the distance between, or the radius of the semicircle. So this is actually the root locus for a second order system written in this form over here. So we already know the answer, but we'll be able now to learn how to draw the root locus for any kind of system that can be written in the canonical form. Okay, before going on with describing step 2, I just want to point out something about the actual solution of the characteristic equations in terms of what it means to solve the characteristic equation and using complex numbers, because remember, S is a complex number. So when we solve 1 plus k times n over d equals 0, we can also rewrite it as k, times n over d equal to minus 1. I've just taken plus 1 and put it and brought it on the right hand side of the equation. Now, k times n over d is a function of s. S is a complex number, so this whole number on the left-hand side is a complex number, generally speaking. But this on the left-hand side has to be equal to whatever we have on the right-hand side, which is minus 1, which happens to be a real number. But a real number is just a particular case of a complex number. So when you're equating two complex numbers, you're actually solving for two unknowns. And why is that? Well, that's because your solution S has a real and an imaginary part. So although the function k times n over d has to be real, but the values for which this happens, that is the poles, might be in general, they might be complex conjugates. So S has a real part and an imaginary part. And so when we write it as sigma plus I omega, this is the Cartesian representation of a complex number. So the two unknowns that we want to find are sigma and omega. However, remember that a complex number can also be written in the so-called polar form. So in a polar form, a complex number is given by a magnitude. You have to think about a complex number in the polar form as a vector, starting from the origin of the complex plane. So rho is the magnitude of the vector, and then you have e to the power of I omega, Euler formula, and omega is the phase associated with the complex number. So in this case, the two unknowns that we need to determine are rho and theta. The two representations of the same complex number are equivalent. In other words, if our complex number is right here, S is a point on the complex plane, then sigma is the real part, or the x component, and omega is the y component, or the imaginary part. But S, if we draw a vector from the origin to the point S, then the length of this vector is rho, and the angle that it makes with the positive real axis is called the phase, or in this case, we've called it theta. So it's the same representation. Sorry, it's the same complex number with two different representations, either the Cartesian one or the polar one. That's why at the very beginning of the course, I told you, go and review your complex numbers, because it is essential that you have a good understanding of complex numbers. And if you haven't done it yet, please take a look at the at the material that I've linked in page 1 or page for week number 1, you'll see useful material to review the complex numbers. If you don't remember anything, if you find it very confusing, please ask me, come to office hours. Few of you have come to office hours, and it kind of worries me because then things are going to get complicated or might get complicated. I don't want to scare you, but I want to make sure that your understanding is clear, because then things will start to accumulate. So don't wait till the very last day to start studying, because it's going to be overwhelming otherwise. All right. So what is the relationship between the two Cartesian coordinates, that is sigma and omega, with the two polar coordinates, that is rho and theta? Well, rho is simply the square root of sigma squared plus omega squared. Pythagorean theorem. What about the phase? Well, the phase is arctangent of the imaginary part, that is omega, over the real part, that is sigma. Very important that you remember this. So magnitude is given by square root of the real part squared plus the imaginary part squared. Phase is arctangent of imaginary part over the real part. I'm going to talk a little bit more about the function arctangent later on. I hope I can do it today, otherwise next time, because you have to be careful of the signs of the numerator and the denominator when you calculate arctangent. So anyhow, whether you choose the Cartesian approach or the polar approach, you still have two unknowns to determine. And so having two unknowns, we need to determine two linearly independent equations. So if we consider the characteristic equation in a polar, from a polar coordinate perspective, you want the magnitude of the left-hand side to be equal to the magnitude of the right-hand side, and then the phase of the left-hand side to be equal to the phase of the right-hand side of the equation. So what is the magnitude of the left-hand side? Well, we have the magnitude of k times, once again, n over d. And then we'll see later how to determine that, but we want this to be equal to the magnitude of whatever it's on the right-hand side. On the right-hand side, we have simply -1. So what is the magnitude of -1? It is simply 1. And now we have one equation here. The second equation is given by the phase, also known as the phase equation. So we want that the phase, or the angle, which I'm going to indicate with this symbol, this wedge. So the phase associated with whatever we have on the left-hand side has to be equal with the angle associated with -1. What is the angle associated with -1? Well, we can draw it on the S-plane. -1 is right here. So the angle that it makes with the positive real axis is 180, or -180. It's the same thing. It's the same angle. And if we wanted to use the actual arctangent formula, we'll have arctangent of the real part, which is -1, over the imaginary part. Sorry, the other way around. Arctangent of the imaginary part over the real part. So here it's arctangent of 0 over -1. If you just plug it in your calculator, you will find arctangent of 0. And the the answer would be 0. That's what your calculator will give you. But the calculator only gives you values between minus 90 and plus 90 degrees. So it will never give you 180 as a response. So you have to be careful because of the sign of the denominator. And that's why it's always good to draw it on the S-plane. So you know that with the negative real part, you have to be either on the second or on the third quadrant. So you have to add 180 degrees if your denominator is negative to whatever value your calculator is giving you. So in this case, we have 180 degrees. There's one caveat here is that we can have even multiple integers of 180. So since 180 is equal to minus 180, but 180 is also equal to 540 degrees. So we add this second bit plus n times 360, where n is equal to either 0 or plus or minus 1 or plus or minus 2, so on and so forth. So in other words, n belongs to the integer field. Okay, so this was a parenthesis that I wanted to open and now close about what it means to solve the characteristic equation, and in terms of complex numbers. Now, with the root locus, we are not directly solving the equation, because otherwise we would be in case B, just finding the poles. And we kind of want to avoid that. We want to develop a methodology that avoids directly solving the equation. But it's important to keep this in mind because it will come up. All right, so if we just want to stick to drawing the root locus though, the second step is to factor our g of s transfer function, also known as open loop transfer function, in terms of R zeros and L poles. So R is going to be the number of zeros and L is the number of poles of G of S. So I'm going to refer to them as open loop poles and open loop zeros. So how do you factorize the numerator and the denominator? Well, the numerator contains all the zeros. So it's going to be the product, which has this big pi symbol, for I that goes to 1 all the way to R, where R is the number of open loop zeros, as I said. And this has S minus ZI. So in expanded form, maybe it's clear, this is, you just write all the factors, S minus Z1 times S minus Z2 times all the way to S minus ZR, where Z1, Z2, all the way to ZR are all the zeros of G of S. Same thing with the denominator. You want to factorize it using the poles. So here we have G, we're gonna use J equals 1 all the way to L, where L is the number this time of the open loop poles of S minus Pj. So this is also S minus P1 times S minus P2 times S minus PL. So in other words, we're going to rewrite G of S or, K times G of S. It's going to be K times S minus Z1 times S minus Z2 times S minus ZR over S minus P1 times S minus P2 times S minus PL. So I've just rewritten G of S using simple factors, first order factors, that is finding the zeros and the poles of G of S. And so now, if we wanted to actually solve the characteristic equation, again, we have to use two equations, the magnitude and the phase equation. So using the magnitude equation, what is the magnitude of this complex number here? Well, we start with the magnitude of K, which is simply K, and then we have a fraction. So let's first take care of the numerator. So when we have a product like so, then S minus Z1 is a complex number. So you want the magnitude of the first complex number times the magnitude of the second one times all the way with the magnitude of the last one. And at denominator, we do the same thing. It just keeps at the denominator. We have S minus P1 in magnitude times the magnitude of S minus P2 times all the way S minus PL. And that this has to be equal to 1, which is the magnitude of minus 1. Why is the magnitude of K simply K? Well, that's because K is a positive number, or at most equal to 0. So the magnitude of a positive or equal to 0 number is the number itself. Now let's move to the phase equation. So what is the phase of the complex number written in this form? Well, we have to start with the phase associated with the constant K. So we have the phase of K, and K being a constant, it would belong to the numerator. So we're just gonna use a plus sign now, because everything that is on the numerator is going to be added. You add the phase associated with the factors at the numerator. So you have the phase of S minus Z1 plus the phase of S minus Z2 plus all the way to the phase of S minus ZR. And now the phase associated with the complex numbers at the denominator, well, they have to be subtracted. So we have minus the phase of S minus P1 minus phase of S minus P2 minus all the way to the phase of S minus PL. And this has to be equal to the phase of minus 1, which we just seen that has to be equal to 180 plus n 360 degrees, with n being an integer. We can already simplify something in the phase equation, and that is the phase associated with K. The phase associated with K is equal to 0. So we can see it in a couple of ways. We can draw it on the S-plane, which is my favorite way of understanding. So K is a positive number, so it's a positive real number. It's just a constant. So it lies on the positive real axis. So what is the angle that it makes, that the vector, this complex number, makes with the positive real axis? Well, that's just 0. So the phase is 0. If we want to compute it using the arctangent, well, we need the imaginary part of a real number is 0, over the real part itself, which is the number K, but K is positive. So now 0 over something positive is indeed 0. Remember earlier we had 0 over something negative, so we had to add 180, but this time K is positive, so its phase is simply equal to 0. Okay, so here I've added a little bit, but if you want to just stick to the steps for the root locus, all you need to do is to find the open loop poles and zeros. That is the poles and the zeros of G of S. Now, step 3, very easy. We just have to locate such open loop zeros and poles in the complex plane. So just draw them. But here I want to make a couple of considerations which connect the open loop poles and open loop zeros with what we want to find, which are the closed loop poles. And here I'm going to consider two extreme cases. The first one being k equals 0. So when k is equal to 0, as written here, the open loop poles, so the poles of G of S, will coincide with the closed loop poles, so the poles of T of S. So if we select k equals 0, then the closed loop poles will be simply equal to the open loop poles. Let's prove that. It's very easy to do so. So we have our characteristic equation. It's 1 plus k times n over d. And we want this to be equal to 0. Now, if we multiply both sides by d, so we have d plus k n of s equals 0. If k is equal to 0, then the second term will go to 0. So we simply have d of s equals 0. But d of s equals 0 allows us to find the open loop poles. So the closed loop poles are equal to the open loop poles for k that is equal to 0. Remember, k is a parameter that can vary from 0 all the way to plus infinity. So I'm considering the extreme cases. Now, if k is equal to 0, well, we pretty much don't have to compute the closed loop poles because we already have them. They are equal to the open loop poles. What if k goes all the way to infinity? Well, now the closed loop poles, so when k tends to infinity, well, they're going to be equal to the open loop zeros this time. And let's prove it very quickly. Once again, closed loop poles must be solutions of the characteristic equation. Once again, let's multiply everything by d of s. And let's divide everything by k, because k is not 0, so we can do that. So as k tends to infinity, this term, the first term, will tend to 0, leaving us with n of s equals 0. And n of s equals 0 will give us the open loop poles. The open loop 0. So you see that these two are the same for k that tends to infinity. In this green box, every time that you satisfy this equation, well, these are the closed loop poles. But now in this yellow box, n of s equals 0, this gives us the open loop zeros. So you see that for the other extreme case, for which k is driven all the way to plus infinity, closed loop poles coincide with open loop zeros. Then we're going to see examples of this. I just want to cover another couple of steps, that is step 4 and step 5, and then we can apply what we've learned in an actual example. Step number 4, because so far what we've done practically is just rearranging the characteristic equation such that it is written in a canonical form, then factorize G of S in its zeros and poles and place such zeros and poles on the as plane. That's it. That's all we've done. So we need a little bit more. Now, in step four, we are going to determine the number of loci. So loci is the Latin, it's a Latin word, it's a plural of locus. So sometimes I'm going to talk about loci, sometimes I'm going to talk about branches of the root locus, because the root locus is going to have different branches. So how many of them do we have? So the number of separate loci, which I'm going to abbreviate with SL, is going to be the maximum between the open loop zeros and the open loop poles. Remember, we used capital R for the number of open loop zeros and capital L for the number of open loop poles. So the maximum between the two will determine the number of branches. If we have one open loop zero and two open loop poles, the maximum between 1 and 2 is 2. So we have 2 separate loci, or 2 branches of the root locus. Each branch, if we start from k equals 0 and we increase the value of k all the way to infinity, it's like starting from an open loop pole, because that's when k is equal to 0. And then we're going to connect it, a branch of the root locus will connect the open loop pole with an open loop 0, which is what happens when k is all the way to infinity. So as usual, we use the x for the poles, so open loop pole here and open loop 0 with the O. And it's a good practice to indicate the direction of growth for k. So as k increases, we start at k equals 0, and this branch will connect an open loop pole with an open loop 0 where k tends to infinity. This is all good, but sometimes, if we have more open loop poles than open loop zeros, then one branch, let's say that we have just another pole over here, then this other branch, yes, starts from this open loop pole, but it doesn't have an open loop 0 to go to. You want to think about, I know it might sound silly, but I think it'll help you remember this. Then poles and zeros, they just want to marry. They're looking for friends. So a pole wants a 0 and a 0 wants a pole. So if we have more open loop poles than open loop zeros, like in this scenario here, then the open loop pole will extend its branch of the root locus all the way to infinity, looking for a 0 at infinity, because it's not there. It's not, we couldn't draw it because it's not there. So it will be there at infinity. Or if there are more open loop zeros than poles, then we will have branches coming from infinity looking for poles. So in other words, if we have more open loop zeros than poles, that is if R is greater than L, then we're going to have R minus L lines or branches that come from infinity. We have more open loop zeros than open loop poles. Vice versa, if we have more open loop poles than open loop zeros, then we're going to have L minus R lines that go to infinity looking for friends. It's going to be clear when we apply these concepts. But always think about there are as many branches as the maximum number of either poles or zeros for the open loop function. So these branches, if they cannot connect, between a zero and a pole, right, in the S-plane where you can see them, then they will go to infinity or come from infinity. So you have line that will go to infinity. All right, another thing that I want to notice, you to notice that the root locus never crosses itself, so you will never find something like this. And you cannot have two branches that share the same line. You will never have segments of two branches together. The only thing that you can have two branches sharing one point, like in the example that we covered here for the second order system. As we will see later, we can consider, as we increase the parameter zeta, one branch collides with the other. I'm not going to color, I'm just going to leave it in blue. But then one goes to the right and the other one goes to the left. So there's only one singularity in which the two branches share a point, and that's when the roots are repeated, the closed loop poles are repeated. But other than that, they cannot both, let's say, go to the right, or both to the left, or both to the right. That cannot happen. Okay. Now that we know how many separate loci we're going to expect, and so we're also expecting how many segments of this root locus will go to infinity or come from infinity. Step number 5, before actually taking care of these branches that go to infinity, step number 5 deals with locating the segments of the real axis that belong to the root locus. In other words, since we are drawing everything in the S-plane, we can take care of the real axis first. So we can color or highlight all the parts of the real axis that belong to the root locus. And in order to do so, we have to follow this rule, which is quite easy to implement, but let's read it together first. So the root locus has real values, that is, it belongs to the real axis, when to the left of an odd number of open loop poles plus open loop zeros. What does that mean? Let's take a look at a very quick example. So let's say that for our system, we have 2 open loop zeros and 3 open loop poles, and they're located right here. So here we have 1 open loop zero, then we have 1 open loop pole. This was just following step number 3. Then we have another couple of complex conjugate open loop poles, and finally another open loop zero here. Totally random, arbitrary, I should say. Now, the trick here is to start all the way from plus infinity, so to the extreme right, and then sweep to the left, following the real axis. So if we do so, I'm coming from far right, but I'm not encountering any open loop poles or zeros until we meet this guy here. It's an open loop 0. So what is the total number now of open loop poles plus open loop zeros? Well, it's just 1, so it's 1. 1 is odd. It's an odd number. So according to the rule, whatever it is to the left of it belongs to the root locus. So until we hit another either open loop pole or open loop zero, whatever is on the real axis belongs to the root locus. Oh, now we've encountered a open loop pole with this X. So now what is the total number of open loop zeros and poles so far? It's 2, because we have the open loop 0 plus the open loop pole. 2 is even. So now whatever it is to the left of it on the real axis does not belong to the root locus. So I'm not going to highlight it. I'm just going to mark it like this, so you see that I'm still going from the right to the left. Well, actually, I should stop here because we have a couple of open loop poles. So now the total number is 1, 2, plus 2 is 4. 4 is once again an even number, so whatever is to the left of this pair of complex conjugate open loop poles does not belong to the root locus. So we still proceed towards the left, and finally we encounter the last open loop 0. So now the total number of open loop zeros plus open loop poles is 5. 5 is odd, so whatever is to the left of it belongs to the root locus. Obviously, on the real axis, we're still referring to that. So in this case, we can highlight all the real axis, and actually here we're going to minus infinity. So to recap, the parts of the real axis that belong to the root locus are the ones highlighted in green. So we can already try and see in which directions the root locus grows. We know that at the open loop poles, k is equal to 0. So we have k equals 0 here, here, and here. And at the open loop zeros, we have k tends to infinity. So the direction of growth is actually, it's natural to think that we go from this open loop pole to this open loop 0. So we go from the right to the left, sorry, to the left, from the left to the right. And on this other branch, we're coming from infinity to reach our open loop 0. So in this case, the open loop pole would be at minus infinity. And again here, the arrow represents the direction of growth for the parameter k. All right, so now let's take a look at a couple of examples, starting once again from a second order system. And let's apply all steps from 1 to 5. Well, for the second order system, we've already seen step number 1. And as a matter of fact, we already know the final answer, but let's now go step by step and see and do it a little bit more methodically. So starting from the characteristic equation already written in the canonical forms, we have 1 plus zeta times 2 omega n s over s squared plus omega n squared equals 0. So this is just what I've already written. N of s is 2 omega n times s, and d of s is s squared plus omega n squared. Well, now it's time to factorize these two polynomials. Well, the first one, that is to calculate the open loop zeros and open loop poles. So we simply have to equate both these polynomials to 0. When we take a look at the numerator, that is 2 omega n s equals 0, the only solution, the only root to this equation is s equals 0. So we have one open loop 0 at the origin. And we can write that r is equal to 1. Remember, r is the number of the open loop zeros. Now let's do the same with the d of s. The solutions here are s equals to plus or minus I omega n. You could write it as s minus I omega n times s plus I omega n. So in other words, the two poles, we have two open loop poles at plus or minus I omega n. So the two open loop poles belong to the imaginary axis, and L is equal to 2. So how many separate loci do we have? Well, we have the number of separate loci is equal to the maximum between R and L, that is the maximum between 1 and 2, which is 2. Furthermore, we also know that L is greater than R, and L minus R, 2 minus 1 is, well, equal to 1, that is greater than 0. So we have one branch that will go to infinity. We have one more open loop pole than open loop zeros. So we know that we're going to have one branch out of the two, because we have a total of 2 branches, but one of the 2 will go to infinity. So let's draw what we know. The first thing that we want to do is to locate the open loop zeros and poles on the S-plane. Let's start from the open loop 0. Well, it is at the origin, so we have our circle at the origin. And what about the open loop poles? Well, they are on the imaginary axis. At plus I omega n and minus I omega n. And this is at 0. So what are the values for our parameter? Remember here, we're not using k, we're using zeta as our parameter. So for our open loop 0, we have that zeta will be all the way to infinity. And for the open loop poles, we have that zeta is equal to 0. So in both cases. Now let's highlight the segments of the real axis that belong to the root locus. So let's start from very far right and let's start sweeping to the left, where we're not encountering anything until we hit the imaginary axis. All of a sudden we have 1, 2, and 3. So 3 is an odd number, so whatever is to the left of it belongs to the root locus. And then you see that we don't have any more open loop zeros or poles, so this branch will just continue going to infinity. So this is what we can write so far using steps from 1 to 5. Now we also know that we will have the remaining part of the root locus will look like this. But this is going to be for the next steps. So far, we have located the open loop zeros and poles, and we've located the segments of the real axis that belong to the root locus. Then we also know that since we have one more open loop pole than open loop 0, then we're going to go to infinity, going to infinity. So eventually, this will be the direction of growth. And also, we know that since we have one open loop 0 drawn, then somehow the direction of growth is also going this way. And so at one point, there has to be something here, and we already know the answer. but there's going to be a point in which the two branches collide and they separate. One going to minus infinity and one going towards the origin. Again, it's useful to already know the answer to understand a little bit of what's going on, because that's going to be useful later to interpret or to already visualize very fast what the root locus might be. I know now it's quite early, but always think about what you're doing. Do not just do it robotically, just following the recipe, okay? Because you can just use MATLAB per se to draw the root locus, but you have to understand what you're doing, because in the interpretation is something that you can add, and that's your value as a human being, as an engineer. Otherwise, the computer is there for the calculations. All right, let's take a look at another example, and that's indeed the example at the end of the last lecture, that is the laser gun. And let's try to draw the root locus, at least using step 1 through 5. Let's see what we can draw. Let's recall that the characteristic equation was 1 plus k times 1 over s plus 1 times s plus 2 times s plus 3 times s plus 4, all equals to 0. So here it's very convenient because the characteristic equation, it's already written in the canonical form and it's already factorized. So steps 1 and 2 already taken care of. However, let's write down the actual values for the open loop zeros and poles. N of s is simply 1. So if we equate it to 0, this doesn't have any solution. In other words, we don't have any open loop zeros, or r is equal to 0. However, the open loop poles, we have 4 of them. We have P1 is equal to -1, P2 is equal to -2, P3 to -3, and P4 to -4. And therefore, L is equal to 4. So how many branches of the root locus are we going to have? Well, that's the maximum between 0 and 4, which is definitely equal to 4. Furthermore, we have more poles, more open loop poles than open loop zeros. L minus R is equal to 4. So all 4 branches of the root locus will go to infinity. Because we don't have any open loop zeros, so the open loop poles are said, all of them will have to go to infinity looking for their friends, for their better halves. Okay, so let's draw what we know. So actually what we know is the location of the open loop poles. One is at -1. Another one is -2, -3, and -4. What else? Segments of the real axis that belong to the root locus. Again, swiping from the far right towards the left, we first encounter -1. -1, we only have 1 open loop pole. 1 is an odd number, so whatever is to the left of it belongs to the root locus until we hit the other open loop pole. Now we have a total number of 2. 2 is even, so whatever it is to the left of it does not belong until we hit -3. Now we have a total number of 3 open loop poles. 3 is odd, so to the left we have a segment that belongs. We hit -4. Now we have a grand total of 4. 4 is even, so to the left nothing belongs to the root locus on the real axis. So here it seems that this is it, but the problem is that for all these values, since they are open loop poles, we have that k is equal to 0. So when In other words, when we take the characteristic equation and what you would need to do is actually rewrite it as in this form when k is equal to 0, otherwise it doesn't really make sense. This is equivalent. So if you use k equals 0, then you have to solve s plus 1 times s plus 2 times s plus 3 times s plus 4 equals 0. And so the four roots are the four closed loop poles, and they coincide with the open loop poles, -1, -2, -3, -4. That's quite straightforward. But then if we increase k, then well, we're going to have different values of the closed loop poles. So we are going to move away from the poles, and I'm using, well, we have to go in this directions because we cannot really go on the other side. So we have to follow these directions that I pointed, these arrows. But what happens now, again, we don't know really how to do it, but if you think about it, now these two branches will collide because there's one branch starting from -4 and then one branch from -3, then they will collide, and most likely they collide in the middle. So they cannot coexist. So most likely one will just go out one way, and the other will just go out this way. So they break away from the real axis, and similarly from the other two, one grows one way to the right, and the other one, let's use this color, grows, as k grows obviously, towards the left. Then the meet in the middle, and one will go away in one direction and the other one will break away in another direction. And so I'm predicting that these four branches will go to infinity following some sort of lines that we'll see later, and they're called asymptotes. And another thing that we could already predict is the fact that you see these branches eventually, at least these two, the light blue and the magenta one, they will intersect with the imaginary axis. And so since we're dealing with closed loop poles, then the real part of the closed loop poles will determine the stability. And as we intersect, as we cross the imaginary line, then we are changing the stability characteristics of our closed loop system. In particular, we're switching from being stable to being unstable. And we already know that at this point over here, we're going to have k is equal to 126, because that was the key value that we found using Routh-Hurwitz. Okay, so the last thing that I want to see today is step 6, and that talks about exactly the lines that the branches are following if they go or come from infinity. So either ways, this happens when R is different from L. So if we have either more open loop poles than open loop zeros, or more open loop zeros than open loop poles, then the branches of the root locus will come or go from infinity following asymptotes. Asymptotes are, for the root locus, are straight lines that do not necessarily belong to the root locus itself. So we just have to draw these lines as, well, guidelines for the root locus, but the asymptotes might not belong to the root locus. They might, there's actually only one asymptote that can belong to the root locus, as we will see soon, but usually they don't. And another characteristic about these straight lines that function as asymptote is that, well, first of all, how many of them do we have? Well, we have a number of asymptotes are, the absolute value between R minus L. Whatever, if we have, let's say, 2 more open loop poles than open loop zeros, then the asymptotes are 2. If we have 2 more open loop zeros than poles, we still have 2 asymptotes. So how do they look like? They are straight lines with a common center, which is usually called sigma A and is known as asymptote centroid. And they are equally angularly separated. What does that mean? We'll see very, very soon what that means. But first of all, let's calculate this asymptote centroid so we know where to center these asymptotes. So here we have a formula for calculating this asymptote centroid. And the good thing is that this is a real value. And that is obviously a real value because the root locus has to be symmetric with respect to the real axis. Why is that? It's because what are we doing? We're just plotting all the possible solutions of the closed loop system poles. And the poles are roots of a polynomial with real coefficients. So according to the theorem, the fundamental theorem of algebra, the roots must be either real, or if complex, they must come in pairs of complex conjugates. So the whole root locus, having all the possible solutions of such roots, well, that also has to be symmetric with respect to the real axis. All right. So what is how do we calculate this asymptote centroid? So we need to sum up all the values of the poles, so P1 plus P2 plus all the way to PL, and then minus all the sum of the zeros. And we divide this by the magnitude of, or absolute value of R minus L. A quick example, if we had P1 equals to 3 minus 2i and P2 is 3 plus 2i, and then we have one, no, let's say we don't have any zeros, so sigma A is equal to 3 minus 2i plus 3 plus 2i. You see that since all the either open loop poles or zeros are complex conjugate, their imaginary part will cancel out. So in this case, the centroid is placed at +6. Then the angles are measured with respect to the positive real axis. And we're going to call it phi of A for asymptotes. And there's also a formula for this. So all the angles are given by 2m plus 1 over magnitude of R minus L times 180. So this gives you an angle in degrees. And m is 0, 1, 2, all the way to absolute value R minus L minus 1. It's easier actually to visualize the asymptotes for specific examples, because usually you have 1, 2, 3, or 4 asymptotes at most. You're not going to find more than that. It's unlikely, especially in this class, you're not going to find more than 4. So why don't we study these 4 cases as an example? So if, let's say, L minus R is equal to 1, then the angle is 180. So the asymptote is just the real axis that goes all the way to minus infinity. That's why the 180. And might have our asymptote centroid here, but it doesn't really matter where it's located, because even if it was located here, then the asymptote is still the negative real axis. It still go to minus infinity. So when you have one more pole than 0, then you'll always have a branch going to minus infinity. Of course, if you had R minus L equal to 1, you still have the same configuration, but now you're coming from minus infinity. So it's just the direction of the growth of K is reversed. So for these 4 examples, I'm just using extra open loop poles than zeros. If you had instead more zeros than poles, you just have to reverse the direction that I'm drawing. All right, so now if we have L minus R that is equal to 2, then the 2 angles are going to be 90 and 270. So the 2 asymptotes are going to be looking like this. And what is this value? This is the asymptote centroid. So you can see that one angle is 90 and the other angle is 270. What about 3 asymptotes? Well, the angles are going to be 60, 180, and 300, but it's easier to remember how they look like. So they're equally spaced, and now the angle between 2 asymptotes is 120 degrees. So they look like so. And remember that the asymptotes do not necessarily belong to the root locus. So for 3 here, we have the 60, 180, and 300 degrees. See, there's always symmetry with respect to the real axis. And finally, last case, if L minus R is equal to 4, then we have the 4 angles are 45, 135, 225, and 315. Or you can also write plus or minus 45 degrees and plus or minus 135 degrees. In this case, you have the asymptotes look like this. So you have 45 and minus 45 plus 135 and minus 135. All right, so just going back to the example that we were seeing right here for the laser gun, we have L minus 4 is equal 4. So the asymptote centroid is equal to -1, -2, -3, -4 divided by 4. So we have minus 2.5 right here. You see that this doesn't belong to the locus. And the asymptotes being 4, they are in the cross, shaped like a cross. And you see here that I'm following this asymptote going to infinity, this way, and then this way. I have to redraw the intersections. And this way. Going like so. So it gives you a direction to follow for the branches. So you know you're going to follow the asymptotes. Then next time we're going to see a few more things, that is always taking into consideration this example, the intersections with the imaginary axis and the locations for breakaway points, like in this case, or break-in points if you're coming from the direction is reversed. And then we're going to take a look at a few more examples, but that's pretty much it. We have to cover break-in, breakaway points, intersections with the imaginary axis, and that's it. So this is all for today, and I'll see you virtually next time. Take care.